Alright, so good afternoon everyone. So today we'll be looking at electrochemistry, right? And I'm going to use a technique. So I'm not going to really follow a teaching pattern today. I'm just going to really just give it in a wholesome way so you can remember it. So I'm just going to come up with a little mnemonic song slash type of stuff for you to remember the whole anode, cathode, and then we'll just teach it random until. So I hope you have read the topic so you will know the basic ideas, alright? Alright, so the first thing I wanted to repeat after me, the movements of electrons in an electrolytic cell is as easy as ABC. You remember that, Macaulay? The movements of electrons in an electrolytic cell is as easy as ABC, whereas A is for the anode, B is for the battery, and C is for the cathode. Clear? And with that concept, as we go along, you will see that you will always remember it in the exam. Alright? But remember that what I'm just telling you is like a mnemonic type of thing. It's not something to write on the exam. Alright? So this is a disclaimer. This is not to write on the exam. Alright? The movement of electrons for the anode, B is for the battery, afternoon. Alright, so the sparks. The movement of electrons in an electrolytic cell is as easy as ABC, where A is for the anode, B is for the battery, and C is for the cathode. Clear? It's not something to write in the exam, it's something for you to remember it when we are drawing these cells. Alright? And remember, an electrolytic cell is basically a cell with a battery, two electrodes, an electrolyte. Right, an electrolyte, when we say electrolyte, we mean a solution or a liquid that can conduct electricity. So it's either a solution of molten ions or an aqueous solution of an ionic compound, which ions in solution can move. Alright? So there's a slight difference between electrochemical cell and electrolytic cell. But remember that at this level, it's strictly electrolytic cell we're going to use. So you're going to have a battery connected to two wires, connected to two electrodes, and we're going to place it into a solution, an ionic solution or a molten solution. Alright? So remember, the movement of electrons in an electrolytic cell is as easy as ABC, where A is for the anode, B is for the battery, and C is for the cathode. Alright? And then with this movements of electrons concept, we're going to take to determine which is the positive, which is the negative, which ions go to which electrodes. Alright? In the liquid. Alright? Alright, so next thing I'm going to draw an electrolytic cell. I remember that with electrochemistry is going to overlap with some quantitative electrochemistry, which I'm going to use calculations, and it's going to overlap with mole concept of both with mass and volume of gases. So that's how complex today we'll get. Alright? So example of an electrolytic cell. Normally we have the beaker with the electrolyte. This is an electrolyte. Right? Then we're going to put two electrodes. So this diagram is a diagram in which you should practice to draw. Alright? Alright? So remember that, as I said before, anode, I'll keep the anode on the left. So ABC, just simply use that pattern, ABC. So anode, then this is the battery. Right? And then so the electrons are going to move in this direction. So E minus for electrons. So it passes through the battery as well, the electrons. And if you don't doing physics as well, you know that electrons move in one direction and the current move in the opposite direction. Alright, but this chemistry is not the class for those stuff, it's physics, alright? Cathode, right? So it simply means that the electrons are moving over here. It simply means that the cathode is going to be the negative electrode. Right? The anode is going to be the positive. This is a plus, this is a negative. Alright? This simply means that this is the positive terminal for the battery, this is the negative terminal, right? So if we know how like a little Duracell look, the positive side is normally the part with the little
flat
bulge. No, the flat part is the negative.
Oh, you say positive.
Good, alright? So as you can see here, the electrons are moving from the anode, which is over here on the left hand side, moving through the circuit, goes through the battery, and to the cathode. Clear? Good. So it simply means that this electrode is positive. Alright? Now, what are some examples of electrolytes? So we have two types of substance can be electrolyte. Either an aqueous solution of any compound, or molten ionic compound. So I want you to take that from the board as well, alright? And Mr. Johnson, you see the introduction which I have to repeat now, alright? So I want you to repeat this. The movements of electrons in an electrolytic cell is as easy as A, B, C, where the A is for the anode, the B is for the battery, and the C is for the cathode, alright? So as you can see here, this is an example of an electrolytic cell, and you have to be familiar and get comfortable in drawing this cell in the exam, right? So this is an electrode, which is the anode. So this is where this is electrode, which is the anode. Over here is also another electrode, which is the cathode, right? So this here is the anode. This here is the cathode. This is the wire that connects the battery to the anode and the cathode. And as I said before, the concept that I'm giving is that the movements of electrons in an electrolytic cell is as easy as A, B, C. Simple means that they move from the anode to the cathode via the battery. Alright? So that is why I put electron movement here. Because sometimes in the exam they'll ask you to show which direction the electrons move. Alright? And to label it anode, cathode, battery, electrolytes, etc. Right? Now, so electrolyte can be an aqueous solution of an ionic compound. Give me an example of an aqueous solution of an ionic compound.
Copper sulfate.
Copper sulfate in solution, AQ. Alright, so if this we have copper sulfate crystals and we dissolve it in water, that becomes an aqueous solution of an ionic compound, and that's an example of an electrolyte. Right? You can also have molten solution. So if for example we have the pure copper sulfate and we should melt it, so we should heat the copper sulfate until it reaches the boiling point. So we're not going to place it in any water. We're just going to put it in by itself and heat it until it actually becomes a liquid. That will also act as an electrolyte as well. Alright? And remember that when we're doing the extraction of aluminum, it's actually an electrolysis process, and it was actually a molten solution, molten mixture of the aluminum salt. Alright, so you can revisit the inorganic chemistry when we actually introduce the electrochemistry then. Alright? Now, if you take an example here, if we have an aqueous solution as the electrolyte, we have 4 different ions that are going to be in solution. Do you have this diagram? We need to. Alright, so the introduction to this class was the movement of electrons in an electrolytic cell is as easy as A, B, C, where A is for the anode, B is for the battery, and C is for the cathode. Alright, I want you guys to remember that. I'll repeat it as I go along. Right? But the disclaimer is that that is not something to write on the exam, it's just something for you to remember how to draw and label the diagram and to understand which reaction is taking place at each electrode. Alright? So example of electrolyte, like an aqueous ionic compound. For example, as I said before, copper sulfate solution AQ. In this, we're going to have copper 2 plus ions. We're going to have sulfate 2 minus ions, right? However, when we dissolve a ionic compound in water, the water tends to ionize a little more. So you're going to have H plus ions there as well, and OH minus ions in solution as well, right? So that is why whenever we have an aqueous solution of an ionic compound in solution, it's going to be 2 cations are going to be in solution and 2 anions, right? Because what happens is that the water is going to ionize to an extent which is going to become significant. If we have water and we're trying to do electrolysis with water, it's actually a very, very poor electrolyte, so it doesn't really ionize much. But if we should dissolve an ionic compound or acid or a base in the water, then the ions and the protons, hydrogen ions in the water now become significant. Alright? Alright, so 2 molten ionic compound. Right? For example, lead bromide. Right? So this would be only have Pb2 plus ions and Br minus ions. Right? So as you can see, if we are supposed to do an electrolysis with molten solution of ionic compound lead bromide, we wouldn't have any issue in which compound should go, which ion should go to the anode and which should go to the cathode. It would be only lead and bromide ion can go to the anode or the cathode, right? When we have an aqueous electrolyte, it simply means that we're going to have more than one cation, more than one anion in solution. So there's a set of rules which is going to govern which anion and which cation is discharged at the anode or the cathode. Alright? So alright, so let's trick back. So the anode and the cathode, right? So remember that as I said before, the cathode was positively charged, the anode, no, the cathode negatively charged, the anode positively charged, right? Because remember that electrons are moving, the battery is pushing the electrons from anode to cathode. So the electrons are going over to the cathode, that is why it's negatively charged. So the cathode is going to attract the positively charged ions, right? So if, for example, that are the cations, so for example, if you have a electrolysis going on like copper sulfate, the ions that would move towards the cathode would be the copper 2 plus and the hydrogen plus, right? Because that electrode is negatively charged, so it would attract the positive cations, right? While the anode is positively charged, it would attract the negative ions, which are anions. Clear, you have to bear that in mind as well, alright? So that's the information about the electrolytes. Right? So electrolytes. Good. So remember that electrolyte, as I said before, is a ionic component dissolved in solution or in the liquid state that it's molten, right? So it's able to allow electricity to pass through, right? Just like how metal would allow electricity to pass through, but it's a different principle. In the metal is the sea of electrons in the metal, which is allowing the electricity to pass through that metal, right? But in a electrolyte, molten state, it's actually the cations and the anions are decomposing and carrying out a chemical reaction to allow the electricity to pass through, right? Alright, so factors. Discharge at, so anion negatively charged at the anode, right? Following? So one is gonna be whether the anode is active or inactive, right? Alright? Now, an active electrode or an anode is one that can take part in the electrochemical reaction, right? While an inert or inactive electrode is like platinum or graphite, which don't normally take part in these reactions, right? So they are inert because they don't normally take part in this chemical reaction, right? Because as we are going to discuss further, whenever we carry out that electrochemical reaction, the electrode itself in some cases can actually, what should I say, dissolve or ionize and go in solution instead of the ions attached to the electrode. Alright? So one of the factors will determine whether it's active or it's an inert electrode, right? Because in some cases, example, copper sulfate, AQ. If we use graphite electrode for both the anode and the cathode, then what happens is that the anode will not take part in the reaction, right? However, if we should use copper as the anode, we find out that the anode itself, instead of the hydroxide or sulfate ion going towards the anode, the copper itself is going to dissolve and go in, ionize and go in solution as copper 2 plus. If we should use a copper electrode which is active. But if we use an inert electrode, then that process will not take place, right?
So,
Listen, alright? Alright, the next factor which will determine which ion will be discharged is actually the concentration. Alright, sorry? Example. Alright? So any solution which contains a halide ion, so the sodium chloride, sodium bromide, sodium iodide, if we have a concentrated solution of sodium chloride, then it's actually the chloride ions that are going to go towards the anode. Right? However, if we have a dilute solution, it's going to be hydroxide ions. Alright, because remember that in a solution of sodium chloride, they have sodium cation, they have hydrogen ion, but they also have sulfate anion and they have hydroxide anion. Alright? Then the third factor is going to be the position of the ion in the electrochemical series. Right, and I'm going to draw the series here for the anions and for the cations, alright? But just take this from the board. So let us look at electrochemical series for both cations and anions, alright? Right? So the rule for this is that the lower the ion is in the electrochemical series, And when we say discharge here, we mean like take place at the reaction at the anode or the cathode. But in this case, for the anions, it would be at the anode. Alright? Alright, so take this for the anions and then I'm going to give you the equivalent series for the cations as well, because it's both of them. But remember that the anions is for the anodes, but the electrochemical series, these would be reactions at the anode. But for the cathode, it would be the electrochemical series for the cations. Alright? So remember that with the anode and the anions, the ion that is discharged there has to do with whether the electrode is active or inactive. If it is a halide ion such as the fluorine, chlorine, bromine, or iodine, it's also going to take into consideration the concentration. And if we don't have those issues, concentration issue, then it's going to be based on the position in the electrochemical series. So most dilute aqueous solution is actually hydroxide ions are going to react instead of the anion from the other solution, right? So as you can see, sulfate, nitrate, sodium chloride, sodium bromide, sodium fluoride, then you can see that at all times the hydroxide ions from the water is actually going to take place at that electrode, right? And actually the equation, the half equation for the hydroxide ion is a very essential equation that you should actually like write down more than one time so you can remember it. So if we change here and put cations, so electrochemical series is very similar to the reactivity series in inorganic chemistry, except that a few of the metals might be flipped. Alright? Because for the reactivity series back in inorganic chemistry, it was group 1, then group 2, then group 3. It's not exactly the case here. Alright? So the highest metal that here is so potassium, calcium. Alright? So it seems that it's group 1, group 2 in period 3. If you want a little kind of stuff to remember. So group 1, group 2, period 3, then group 1, group 2, period 2. Alright? So this is going to be sodium, magnesium. Alright, then group 3, and then the transition metals, of course. Transition metals plus hydrogen. So you have Zn2 plus, Fe2 plus, then you're going to have hydrogen, copper, and silver. Alright? This is some, but you can get the full table from the book. Right? So just remember that we tend to put hydrogen so we can have an idea. Remember that in electrochemical electrolysis, the hydrogen will tend to be discharged at the cathode as well. So we kind of compare the hydrogen is going to behave similar to the metals because it's positively charged as well. Clear?